Good morning. Sorry I'm not here today. I'm going to go over some quick notes with you all about half-life and then work a few practice problems with you so you can complete the rest of your practice problems, and then we can focus on the M&M lab, which will be tomorrow. All right, so first let's define half-life. So half-life is the time that it takes for half of a radioactive substance to decay. Half of a radioactive substance to decay. All right. Now, it doesn't work that neatly. If something has a half-life of, say, 10 hours, then after 10 hours, you don't have exactly 50% of it. But this is a good way to think about how this works. In reality, it's much more probabilistic, whereas, after a half-life time, then there's a 50% probability that half of the sample will have decayed. But when we think about, again, considering practice problems and such, we can think about this as a good model as to how things decay. Okay, so for example, let's say that we started out with 10 grams of something, and let's use that 10 hours as a half-life time. Okay, so after 10 hours, we would have 5 grams of that sample. After another 10 hours, we would have 2.5 grams of that sample. After another 10 hours, we would have 1.25 grams of that sample, and so on and so forth, okay? And so if you want to look at this with the wider lens, you could say that after 1, 2, 3 half-lives, starting with a 10-gram sample, you would wind up with 1.25 grams of that radioactive substance. So eventually, the entire sample will decay. Eventually, the entire sample will decay. All right. So now again, so half-life describes, again, it describes the amount of time that would take for half of a radioactive substance to decay. All right. So an element with a long half-life will obviously decay very slowly, and an element with a short half-life will decay relatively quickly. All right, so a couple examples of that. If you look at your periodic table, potassium 40, so potassium 40, and that would be 19. Okay, this is an example of something that has a really long half-life. It's like somewhere in the neighborhood of like 1.25 billion years. All right. And then we could also look at something like technetium, which is Tc, and that's 99 over 43. So that's number 43 on your periodic table. Technetium has a half-life of about 4 hours. Okay, and so that's a really important isotope that's used for medical applications. If maybe you've heard of a PET scan before, that's used to help, well, amongst other things, help identify cancer in patients. Technetium is really effective for that. It has a really short half-life, so its decay is very noticeable over a short period of time. All right. Okay, so how are half-lives used? Well, scientists can use, and here's another example of one that you may have heard of before. Scientists can use carbon-14 to measure how old something is, and this is going to be like some sort of like I'll probably spell this wrong. This will be like some sort of like archaeological artifact, okay? So it has a half-life of 5,700 years approximately. So this is like pretty effective, like up to about, let's say 70,000 years. Once you get past that, then carbon-14 doesn't work as good, but it's really, really effective up to that point. So just an example of how that's used. Carbon-14 actually goes through beta decay. So scientists can measure the ratio of carbon-14 to what it's, if you think about that, so if it goes through beta decay, all right, so there's 6 protons, so 14 minus 0 is, actually that's not that, that's the daughter, sorry. So 14 minus 0 is 14, and then 6 minus negative 1 is 7. So that's going to be nitrogen 14. So they can look at in a sample the ratio of carbon to nitrogen and get a pretty good idea about how old that sample is, provided it's not more than about 70,000 years, because at that point, the ratio will just get so small, you won't really be able to measure much carbon, okay? Now, how do we solve half-life problems? Okay, so for our first example, we will look at, okay, so the half-life of zinc 71 is 2.4 minutes, so that's a very short half-life. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes have elapsed? Okay, so our half-life is 2.4 minutes, so you have our knowns and unknowns written. Our total time is 7.2 minutes, and our starting amount is 100 grams, okay? So the first thing that we want to do is we want to find the number of half-lives, and sorry this is broken here, it'll be not broken on your page. Find the number of half-lives that this substance goes through. So we're going to take the number of half-lives divided by half-life time, okay? So we're going to take time divided by half-life time, okay? So we're going to say 7.2 minutes divided by 2.4 minutes, and that is, it should be a small whole number. Okay, so that's going to be equal to 3 half-lives, okay? So that's going to be 3 half-lives, all right? So when you figure out the number of half-lives in our class, so for the next couple days as we do this, if you get anything other than a small whole number, then you probably did something wrong and you might want to recalculate, okay? This is going to be pretty simple, all right? So step 3 is we just write the decay amounts. Now the way that we do that is we begin with our starting amount, so that's 100 grams, so that goes here, and we decay it 3 times, okay, because it goes through 3 half-lives. Now remember, each half-life time is 2.4 minutes, so we can draw an arrow and we can put a little 2.4 here to show that that's 1 half-life. So 100 goes to 50, and another 2.4, 50 goes to 25, and another 2.4, 25 goes to 12.5, okay, and that's going to be grams, and that's what we will end up with, okay? So after 3 half-lives, we will have, and starting with a start amount of 100 grams, we will have 12.5 grams of, zinc 71, okay? All right, one more, and then I'll turn you loose. Okay, now this time we're going to actually calculate time. So we're going to, instead of calculating end amount, we're going to actually now calculate time. So let's say that we have 80 grams of an isotope with a half-life of 36 hours. So how much time will have elapsed when only 5 grams remains? Okay, so your half-life is 36 hours. Okay, your total time, that's what we don't know. And your start amount is, let's see, 80.0 grams, and then your end amount is 5.00 grams, okay? And you know, the decimals really probably aren't necessary here, okay? All right, so that's step 1, writing the knowns and unknowns, like always. Okay, step 2, we're gonna write the decay amounts to determine the number of half-lives that the substance goes through, okay? So we're gonna kind of do this in reverse a little bit. That may seem difficult, but actually it's not, because we have the end amount and we also have the start amount, okay? So if we take the start amount and we just start to decay it, now remember, when we decay it, it just reduces by half each half-life time, okay? So 36 hours, 80 turns into 40. After another 36 hours, 40 turns into 20. After another 36 hours, 20 turns into 10. And after another 36 hours, 10 turns into 5. Okay? And so that's that 5 gram, that's that end amount number that we're looking for. All right? You see that? There you go. Sorry. Okay, so we end up with that 5 grams, okay? So then step 3, we find the time it took for this decay to take place. So we need to just do 2 things here. Okay, first we need to figure out how many half-lives have passed. So we just count our 36-hour intervals, 1, 2, 3, and 4. And next, we just need to multiply this number by our half-life time. Okay, so 36 times 4, and that's going to be equal to I think it's 144, but let's see. 36 times 4. Yep, 144. Okay, so the time that it would take for this isotope that you start with 80 grams, end up with 5 grams, and has a half-life of 36 hours, it's going to take it 144 hours to get to that point. Okay? All right. So there are some practice problems on the back. Let's work on those. And yeah, send me a Schoology message if you have any questions. There are some Khan Academy videos on this, but they're a little bit more complex than what we're doing. If you just Google half-life time, like simple half-life time problems, then you might be able to get something that's a little bit more manageable. Okay, so if you need that, you can do that. But otherwise, this video lasted 11 minutes, so that should give you, I don't know, probably 30 minutes or so to work on this, and that should be plenty of time. All right, outstanding. Make sure you check your answers on your decay problems from yesterday, and I will see you all tomorrow. Thanks.